Good afternoon. My name is Miguel Molina Solana, and I'm going to introduce you to our vision towards data-driven simulation models for building energy management. The outline of today's presentation begins with a brief motivation of the problem at hand. I will then introduce you to two approaches for optimizing the control of the equipment of a building in terms of energy. Those two approaches will converge in the need of having building simulation models that can run quickly. To that end, we introduce the use of deep learning for simulation, or as we call it, deep data-driven simulations. I will conclude the presentation with some conclusions and lines of further work. The use of simulation software will imply a business volume of over $2.5 million US in 2025, with more than 100,000 companies using it. These are actually great numbers, but running simulations of physical phenomena is costly, as it often requires manual coding of the relations between inputs and outputs, and it's time and resource intensive. It is therefore almost impossible to run these simulations interactively and use their outputs for decision-making in real time. If we focus on energy behavior of buildings, a simulation model characterizes the response of the building to the action of the equipment and the environmental conditions. That characterization is encoded through several differential equations that reproduce the energy transfer laws. These simulation models are built with specialized applications used by knowledgeable experts. The good news is that if we can have simulation model of a building, we can actually use it to test many what-if scenarios and learn from them, checking how much energy is spent and how is the comfort maintained. Two approaches have been used for that learning. First one, model predictive control, which is the classical one, and reinforcement learning, which has gained great traction in the last decade. Without further ado, let's briefly touch on both of them. Model predictive control requires a simulation model against which to test different actions. It allows us to create longer-term operation plans, not limited to just reactive actions, but adding sort of a plan. The issue with model predictive control is that it is a combinatorial optimization problem. We choose a low complexity model, we limit the number of variables involved, which is good in terms of efficiency, but reduces the capability of the control and the possible interactions, sometimes becoming a very simplistic view of the reality. However, if we opt for a full complexity model with more variables and interactions, we can achieve higher accuracy and more interpretability, as it is more alike the real building. However, the cost is that we lose efficiency, making in some cases unfeasible to run very detailed simulations. We actually tried the model predictive control approach in this European project, Energy in Time, which finished it in 2017. We developed full complexity models that were able to achieve energy savings of around 20% in average, reaching in some cases, in some scenarios, to 40%. The following slides, there are some results extracted from one of the papers that we published, which is this one reference here. I'm not going to spend time on these slides, but you can check the paper if you want. So actually, this is interesting. What we see here is that the system we developed was particularly good on weekends, which is these values here. The reason for that is that during weekends, human operators were not actively in charge of the building. However, during weekdays, although there are some small improvements between the human operator and and our system, results are generally very, very similar, and in some cases even worse. All in all, the model predictive control approach has its limitations. The main one is that it depends on the creation and running of a simulation model, which is often non-trivial and very time-consuming. Because we often tend to overcome this by relying on low complexity models, the ability of testing alternatives and propose new strategies is often limited, as is dealing with evolving conditions. In the literature, some alternative solutions have been offered, and of particular interest are those based on deep learning. In our group, we're actually embracing two of them that can go together. The first one is to replace classic model predictive control with deep reinforcement learning. And the second one is using data-driven simulation models, for which you have more details in our paper in the conference. Reinforcement learning has seen a great interest in the last decade due to its coupling with deep learning and leading to what we know as deep reinforcement learning. It has been used in many different problems, with some of the most known being the Atari games or the AlphaGo game. The basic setup in a reinforcement learning problem involves having an agent that interacts with an environment. And after each interaction, the agent gets some rewards to its actions and some observations about the new state of the environment. This is actually in a loop. So the agent then in the next iteration chooses another action, state, receive another reward, get some observations, and so on and so forth. We can actually add deep learning to this framework, for instance, with networks for estimating the reward or to select the next action. The way to formalize these problems as follows. Basically, the goal is to minimize energy while maintaining temperature or any other metric within a desired range by applying a sequence of set points to the equipment. So in this case, the state is time, temperature, and any other sensors. The action that the agent takes is a combination of different set points, and the reward, which is here, in the case of buildings, is actually a weighted combination of two things. The first one is the cost of the energy that is necessary to run the equipment, and the second part of the reward is actually a penalty for violating comfort. We assume that the environment is a simulation model of the building. In this slide, you can see the general framework of a building control problem, as was published by Wei et al. Basically, what these guys did was taking the original Atari paper and translate it to the domain of building energy control. One of our MSc students at Imperial College also proposed and implemented her own deep reinforcement learning architecture for this problem, the reference here. But all in all, the point is that for learning, in this deep reinforcement learning scenario, there are several approaches, more or less complex, that takes into account several things or aims at optimizing particular parts of the process. However, there are currently several changes that remain open and needs to be tackled. The first one is that there is currently no such OpenAI engine for energy control. In other words, there is no common environment and API to run deep reinforcement learning for building energy control on it. Second, there is a lack of common scenarios and benchmark to compare performance of different algorithms, some sort of ImageNet for this domain. In our research group, we are currently addressing these two issues by creating Energy, which is a Python package that acts as a gene environment for building energy control and also provides several examples and benchmark so you can compete against it. There are also additional issues that came from real-world control problems that, of course, need to be tackled. And among them, we can cite the limitation of training data, the presence of operational constraints, and particularly the last one, which is the lack of persistence of cheap and fast simulation models, which is our next point in the presentation. So the basic question would be, can we represent a simulation model of a building as a neural network? So let's go to it. Firstly, I would like to say that neural networks have indeed been used to predict energy consumption. And this is a classic example. So as the inputs for the network would be sensors, observations coming from sensors, then you have the network, and the output is the estimated consumption, the next time stamp. So if from that architecture, a simulation model is actually an extension of it. As inputs, we have sensors, and also we have actuators. And as outputs, we have the consumption as before, but also if we have observations, so sensors readings at the next timestamp, then we actually have here what would be a simulation of the building. This architecture actually works fine for short-term prediction, but start to degrade for longer predictions. It is also a black box model. So in other words, it is difficult to know how inputs and outputs are related to each other. So in order to solve the different issues that might arise, different deep learning architecture has been proposed in the literature. And here are a couple of examples applied to the energy domain, try to overcome some of those problems. An additional issue is that these architectures do not take advantage of the underlying physics. So it would be a good idea to add this knowledge of physics and the constraints and restrictions to the network. And that's precisely what the CIAN and SIMNet, which are actually frameworks not related with building energy control, but in general deep learning, aim to do. They aim to include physics-informed learning in the learning of the neural network. However, they are still work in progress because right now they're only based on fully connected networks. So for the current neural network, LSTMs, and other different architecture, they're still not, they cannot still be integrated with them. As a conclusion, what we are aiming for is something that we presented in our 2019 NeurIPS poster, which is namely to add deep learning to this framework in both the control A and also in the simulations B. If we have simulations that run quickly and cheaply, which is something that can be achieved with deep learning, then we can run many simulations, and which is actually good for having an effective reinforcement learning process, because we can try and test many times in different conditions and using different actions and actually get a more optimized plan. However, of course, there are further lines of research to overcome some problems, but also to optimize the learning in particular scenarios. Regarding A, the control part, the main problem to solve is to learn effectively with a limited number of examples. And those examples might not cover all the different scenarios. Imagine if you have a building and you have historical data, it's very, very possible that in your historical data, you haven't had a strange day in terms of weather or some unexpected circumstances. So you don't have an example to actually learn from if that's the case. Regarding B, which is the simulation, and having this simulation model, problems come from not having enough data, again, but also on being able to encode the physics information and the physics constraints. So actually, having the temperature can only be in a particular range, or that there cannot be sudden changes in the temperature, and many other things. It's something that a neural networks per se cannot take into account. So we need to add that information somehow. This is the end of my presentation. If you have any questions or would like to further discuss or collaborate on any points, please get in touch. Thanks and enjoy the rest of the conference.